Good day everyone, this is Triple E131 and for today we will be discussing the last part of the MOSFET module. Mainly, we will be discussing MOS transistor amplifier topologies. So the main highlight for today's discussion is basically characterizing the common amplifier topologies. We have here the common source, the common gate, and the common drain amplifiers. So they are actually analogous to that of the discussion of the BGT amplifier characterization, wherein we will actually be focusing on their characteristic when subjected to a general signal. So we're not imposing any restriction here of the signal size. We will just characterize and we will try to find out their behavior when subjected to any general input. Okay. So for the topologies, we actually have three main topologies. You have here the common source, the common gate, and the common drain. So this is actually quite similar to that of the BGT, and you can say that they're somewhat somehow analogous with each other. It's such that the BGT amplifiers, they have more gain compared to this one, because by inspection or just by looking at their current equation, the MOSFET has an exponential characteristic. Meanwhile, the BGT has an exponential characteristic, while the MOSFET has just a quadratic. So we are actually expecting that this will have lesser gain. So for the first amplifier topology, we have here the common source. So this is the equivalent of the common emitter. So the input, it will be fed into the gate, and the output, it will be taken into the drain. So we have here, this is for the NMOS, and this is for the PMOS. And we have here the common gate. The common gate, the input is in the source, and the output is taken into the drain. And lastly, we have the common drain. The input is taken into the gate, and the output is taken into the source. So again, the common terminal, when we say common gate, common source, this is actually with respect to the time varying AC input. You will actually see that in future discussions when we try to separate the discussion of AC and DC. You will see that they actually have different circuits in such a way that we are trying to superimpose the responses of them. So let's say when we're just dealing with the AC input, we will actually shorten out those any DC sources. That's why the common terminal here, it's actually with respect to the time varying signal. So let's first try to characterize the common source amplifier. We will characterize its voltage transfer characteristic, and we will take the derivative of this to somehow get an idea of what is the gain of this type of amplifier at different biasing points. Okay, so just a review. So the linear equation for an NMOS is actually defined by this equation. So we have here ID. Oops. So we have here ID is equal to the transconductance times VGS minus VTH minus 0.5 VTS times VDS. And when it's saturated, you have here 1/2 Kn VGS minus VTH quantity squared. The PMOS, it's the same, it's just that we have a difference here in the subscript. Instead of GS, it will now be SG, and instead of DS, it will now be SD. Same for the saturated part. Okay, so let's have here an example of a common source amplifier. So we're actually just plotting its output subjected to different inputs. Okay, so let's try to just make sense out of this one. So at zero input, our MOSFET, so if this is 0 volts, we see that VGS is still 0 volts. In that sense, our amplifier is still in cutoff. Therefore, we can impose the condition that ID is still 0. If ID is 0, then you'll see that there's no voltage drop in our RD. Therefore, Vout is still 10 volts. Now for the transition, remember in our discussion that for the transition, we can still impose the condition that ID is equal to 0. So for the transition, it's still transitioning from cutoff to saturation. The current is still 0. So ID is equal to 0. Therefore, our output still is 10 volts. Okay? And then when the VG is big enough, when the VGS voltage here is big enough such that it can cause it not to be in cutoff anymore, it could either be in saturation, but for the transition, you'll actually see that it will transition to saturation instead of linear. The reason for that is the current here is still small. That's why you will actually be expecting that the voltage across your DS junction to be large enough. So if it's large enough, remember, if our DS voltage is large enough, then that actually causes pinch off, and where you're expecting that you are in saturation state. Okay, so in saturation state, it will follow that this amplifier will follow the equation ID is equal to the transconductance times VGS minus VTH quantity squared. So this is for this saturation. Okay, so let me ask you again, guys. I've actually discussed this in our previous classes. It's actually very important that you know how to solve the transition regions. So for this one, for this part, this is actually easy. We just impose the condition that ID is equal to 0. Okay, so that's for that transition. This one is a little bit harder. This will you will actually need to impose a condition here. The condition that we've derived that we need to impose is that we impose that the ID at that transition, so at the SAT to linear transition, is equal to 1 half K 1 half Kn VD S SAT squared. So this is the condition that you are going to impose, and the other equation for you to actually solve this one and this one is the KVL from your source down to your graph. Okay, so from the drain to the source, you just apply KVL and you apply this condition. And from there, you can actually solve your VDS. You can solve the VDS. And then if you solve VDS, you can solve for the IDS at that transition. And lastly, you can actually solve for the output at that transition level. Okay, it's very important that you know how to compute these transitions, because these transitions, remember in our previous exercise, we actually use the transition to calculate the Q point that will provide us with the greatest output swing. Okay, and lastly, if we're going to transition to linear already, this is going to be after that transition, and it will now follow the linear equation. Okay, so the linear equation for the current, for the channel current. All right, so in order for us to get the gain of this, we will just take the derivative of the output voltage output expression with respect to the input voltage. Okay, so in saturation, so the gain is 0. It's when the transistor is cut off, as you can see here. So the derivative of a constant is just 0. So this part here is 0. But in saturation, you'll see that V out here is actually, okay, so V out is equal to the VDD minus RDID. But the expression that you are going to use for this case is the equation for saturation. That's why you have here 1 half Kn VGS minus VTH squared. But take note that VGS here at this part is just your input. Okay, so that's why we have VI minus VTH squared. Now taking the derivative of this with respect to the input, okay, so this doesn't look like my output variable tayo dito, so it's just straight up taking the derivative of this. We get negative RDKN VI minus VTH squared, and then we take the chain rule of that. That's why we have here okay, so square, it happened to the negative. Okay, we're not taking it the derivative of VTH, so there's no chain rules. The chain rule is just 1. Okay, that's why it's negative. So for the linear the saturated part, our gain is given by this expression. Okay, now for the linear region, we have here VDD minus RD, and this is the current expression for the linear region. Now, as you can see here, we now have dependency on V out as well. Okay, because remember, it's actually it's VI minus VTH minus 0.5 VDS. And in this case, VDS is actually our V output. Now, to make this easier, we will actually just make use of implicit differentiation to basically just have a cleaner answer. But let me teach you guys a way to get the implicit differentiation fast without actually doing the implicit na mag-implicit ka pa. So there's actually a shortcut in getting the derivative in the implicit derivative. So say you have here dy over dx. The way you do that is that you just take the negative partial derivative of your function with respect to x, and then you derive that with uh, the partial derivative of your function with respect to y. But the condition for you to use this is that you need your function to be in this form. So a function of x and y that should be equal to a constant. Okay, a constant or zero. Okay, so let's try to solve this one using this expression. Okay, let's just move this here. Oops. All right. Okay, let's just erase it. Just remember that that is the equation. Okay. So in this case, our y is v out, our x is v in. So let's put everything, let's put all the constants to the other side. So the constant would, in this case, it would be VDD. Okay, so that's VDD. VDD is equal to V out plus RD KN VI. Okay, I think it's better if we have another page so it's cleaner. All right, so sorry for that. So we have here VDD is equal to V out plus RDKN VI minus VTH minus 0.5 VO times VO. Okay. So in this case, i-distribute na lang natin yung VO para mas madali. So VO plus RDKN times VI VO minus VTH VO minus 0.5 VO squared. That's equal to VDD. And then remember, I mentioned kanina to get the dy over dx. So in order for us to get the derivative of VO with respect to Vn, we just have to get the partial derivative of this function with respect to Vi, and then partial derivative of that function with respect to VO. So, yung mangyayari dyan is, so let's take the partial derivative of this with respect to Vi. Okay. Oops, this is K, it's supposed to be K. So, in this case, if it's with respect to Vi, so maka-cancel lang yung VO, so that's 0. And then, we'll just treat everything constant if it's not Vi. Okay? So, RDKN is a constant. So, RDKN, that's a constant. And the derivative of this with respect to Vi is technically just VO. And then, wala na tayong Vi here. So, technically, yan lang yung numerator natin. But, don't forget about the negative. The negative. Okay, so that is our expression. Now, for the denominator, let's take the partial derivative of this expression, with respect to V out. So we'll treat the V out as our independent variable, and everything will be constant. So V out in derivative again, that's going to be equal to 1. Then we have here RDKN. And then we have here, so with respect to V out, so yung matitira is VI minus, so with respect to V out minus VTH minus, so that is going to just be equal to V out. Kasi, ibababa natin yung 2, then minus 1. Okay? So, this is now the expression for the gain at the linear region. Okay, so well, you have the option to just basically isolate v out here and do the derivative normally. You can also do the implicit the normal way, or you can just make use of the shortcut of taking the derivative using partial derivative. So I prefer this method because this will already give you the simplified form of the equation. Okay, excuse me. So now, using implicit differentiation or using our shortcut, we can get the derivative or gain to be equal to this. So you now have the two gain expression, I mean basically three, because the gain for the cutoff region, that's going to be 0. We have here this expression, and then we have here this expression. Oh, sorry, ito na pala yun. Yan, this one. Okay, so if we try to plot that, if we try to plot our gain, we see that in the cutoff region, our gain is 0. And then if we if we're already in saturation, it will follow that our expression will be this expression. So that expression, and then to this expression. And then when we transition from saturation to linear, we see that our gain actually starts decreasing until it goes back to 0. So again, as I've mentioned in my discussion way back in BGT, the gain is actually not constant all throughout. Okay, so it's not all throughout. It's not constant all throughout in a way that if you apply a signal, if you bias it here, I suppose you have a signal that basically occupies this region, it will experience different gain. So if your signal is large enough, you will actually experience what we call gain compression or gain expansion in a way that it does not experience gain equally. Okay, so parang mas stretch out yung upper part, and yung baba is mas maliit yung gain na na-experience niya. So that's why if you actually don't want your system to be to have this non-linearity for gain, you somehow restrict your signal to small signals para ma-restrict lang natin yung gain to be relatively constant for that signal. Okay? So yan lang yung disadvantage ng large signal. It doesn't you don't experience a uniform constant gain. Okay? But there's actually a fix for this, and I've also discussed this one. For you to have a relatively linear behavior or a relatively constant gain, you can just apply a source resistor. So by applying a source resistor, it makes your system very linear. So the reason for that is you're somehow applying a feedback network. Okay? So in that case, liliit pa yung gain natin. So our gain is small enough, it will even become smaller. Okay? So yan lang yung disadvantage ng making it linear for large signals. Okay? So yan yung motivation natin why in our future modules we will focus on restricting our signal for small signals, because we know that if we let our signal basically swing from here to here, it will somehow get some harmonic distortion. Okay, so that's for the NMOS common source amplifier. For the PMOS common source amplifier, the analysis will be the same. It's just that magkabaliktad lang yung mga magbabaliktad lang yung everything in a way that GS becomes now SG and DS will now become SD. Okay, so this is our topology. So you can write our V out. So V out in this case is just RD times basically ID. RD times ID. So RDID, and for when in saturation, this is going to be the expression for the current, 1/2 times the transconductance times VDD minus VI. Okay, so VDD minus VI minus VTH squared. Alright. Excuse me. Okay, tama. Kasi nga, VSG. So that's V VDD minus VI minus VTH squared. So, yan yung sa saturation part. For the linear part naman, we will just again change our current expression to the equivalent linear expression. And this is going to be the expression. Okay. And then, if we take again the derivative of that, this is the gain that we're getting. And if we take the derivative of this, is the gain that we're getting. So the gain is actually pretty similar, guys. So you can somehow manipulate this one. Let's try to manipulate this such that meron tayong RDKP here. RDKP, VO minus VDD. Then we have here 1 minus RDKP 1 minus RDKP, and then may negative tayo dito, so ilabas na lang natin yung negative, so we get VI plus VTH minus VO. Okay, so it's somehow similar to the NMOS counterpart. Okay, so I'll leave you this as an exercise so that you can practice the shortcut that we've discussed. So again, the shortcut is just put all constants to the other side and just get the partial derivative with respect to x to get the partial derivative with respect to y, and you divide that. And then don't forget about the negative. So I'll leave you that as an exercise. But the thing that we need to just take a look at here is that the characteristic of a common source is that its gain is actually negative. And you will experience the greatest gain if you bias it nearer to that of the linear region. Okay, so if you bias it such that we're close to the linear region transition, you will experience more gain. Well, the trade-off for that is that you will have less output swing. Okay. Now, let's proceed to the common gate amplifier. For the common gate amplifier, our input is fed into the source, and our output is taken to the drain. So again, the process is going to be the same. We will get the VTC for this and get its derivative. So when it's saturated, same expression. So if it's saturated, this is going to be the current expression, and our output is just VDD minus, so V out is equal to VDD minus IDRD. In that case, this is going to be your expression for V out. For linear, mag-iiba lang ulit yung current, therefore ito yung expression natin for linear. Okay. So let's before we start, let's go through this exercise. Before we characterize the gain of this common gate, let's first go through this common gate amplifier circuit. Let's try to solve this exercise. So determine. This is actually easy, guys. You should know how to solve the circuit using this, but let's try to solve B because that's the more interesting part, solving the transition. If it was me, I would actually solve for this first. So I will solve for this first, and then I will actually solve for A. Because once I know the transition, then I will actually know ano yung mga to. Okay. So the first thing that we impose, actually, what did we mention before? The first thing that we impose when we're at the saturation linear transition is that ID is equal to 1/2. Okay, so 1/2 Kn V. Oh, okay, tama, Kn mo to. Yeah. Okay, so 1/2 Kn VDS sat squared. That is the first. This is the first equation. So, yung ds natin in this case is actually just VO minus VI. Okay, so let's just have that in mind right now. Now, the next equation that you are going to need is actually just this part. This part. Okay, so the next equation is you get VDD minus ID RD minus VDS sat. So I did VDS sat, and that's equal to 0. So this is you now have two equation. Okay, for proper, let's label it as ID set. Let's label it as ID set. So you have two equations, you have two unknowns, then you can actually for solve for the VDS SAT, and once you solve for VDS SAT, you can solve for the ID SAT, and lastly you can solve for VI and VO. So that is going to be the process. I leave that up to you. Try to solve VI and try to solve VI and VO. So I leave that up to you. Try to solve that. I will just upload the solution next meeting. Or basically, let's try to discuss then again next meeting if we show up in class. So this is as a review na then for your exam. Okay, if we try to plot the voltage transfer characteristic of this is what we're going to get. So if it's 0, it's cut off. Then we're going to transition to saturation, and lastly, that's the transition from saturation to linear. And if we try to get the derivative of the voltage expression that we got, this is going to be the expression. Similarly, this is going to be the expression for the linear region. Again, this is very easily done. To get the derivative of this, to get the gain, you just have to take the partial derivative of f with respect to x, and partial derivative of f with respect to y, and take the negative. That's the shortcut. So then, try to practice your derivative skills by applying this one. Okay. And here, the thing that we just have to look at here is that the gain at the saturation region is actually positive compared to that of the common source. So for the common gate, it's actually positive. So it's somehow similar to the common base of the BJT. So their gain is actually quite comparable. They have this same with the BJT, that it's positive. Okay. But the thing here, okay, hindi din pala to similar to BJT. Okay, the thing here is that this is actually the common gate actually is a current buffer, in a way that your current at your input actually remains the same to that of your output. So this is a current buffer amplifier, and it's actually also a good voltage amplifier. For the common drain, this is similar to that of the common collector in such a way that this should be a voltage buffer. So dapat 1 yung makukuha natin somehow na gain. So the process will be the same to get the V out. So V out is RDID. This is the expression. So that's the expression for saturation. For linear naman, this is still RDID. However, the expression is now going to be the same. This one. For this part, this is the saturation part. This is the cutoff, and this is the part wherein it was linear. And if we take the derivative of that, this is the expression that we are going to get. So for the saturation region and for the linear region. So let's try to take a look. Why is this actually somehow equal to 1? So, it's actually very easy. You will see that if this term is much larger than 1, this term is much larger than 1, then, okay, so this is in the thousands, this is in the milli, and then you have here some in the, so it's not really that large. So as you can see, it's not that of a good voltage buffer. Kasi yung voltage buffer kasi, mas malaki yung gain mo, mas malaki yung gain ng device mo, mas maganda yung buffering niya. But good enough na ito, now you can just approximate this. So very crude approximation. Now we can approximate this one to be larger than 1, much larger than 1, and therefore this will dominate, this term will dominate. Then you can approximate this as 1. So if you try to graph that, approximately equal to 1. As I've mentioned, the gain of your common drain, it's not of your MOSFET, is not that big. Unlike the BGT, where your drain is actually large, such that yung buffering natin, that was actually very good. Now we can basically just approximate our gain to be equal to 1. For the common drain, it's a different story. the gain of the MOSFET is quite small, such that we don't quite actually approach one. But that is actually the goal, to just somehow approach one. In this case, it's going to be less than one even. Okay, and for here, this is going to be uh, the gain at the linear region. Okay. So for applying and retrieving the output, we actually make use of uh, coupling capacitors. And again, our discussion a while ago, we actually just um, so parang kasama na din yung bias doon. But whenever we're actually trying to amplify small signals, or trying to we want to set an operating condition, and we do that by providing the proper bias. And once we provide the proper bias, and that's when we superimpose your input. And this is how you get your output as well, so that you actually isolate the DC part of your output, and you just get the time varying part. So that's how you apply and you take the output of your amplifier circuits. Okay. So for the BGT versus for the MOS amplifier, for the common emitter and common source, they both have negative gain. The common emitter has a larger gain than common source, which is expected because it's a BGT. It's an exponential yung current equation niya. For the common base and common gate, they both have positive gain. The magnitude of the gain is comparable to the common emitter and the common source counterparts. It's just that it's a positive counterpart. Lastly, for the common collector and the common drain, they have a gain of 1, slightly lower for common drain. Because again, it has a lower gain. Parang yung amplifier, yung MOSFET mo, it has a lower gain. That's parang hindi niya ma-achieve talaga yung buffering na good as well. So, in terms of performance, this is what you prefer for uh, voltage buffer. Pero may advantage din to. Yung advantage nito is that it provides very good input impedance. So actually, MOSFETs in general, they provide good input impedance. But what do you mean by input impedance? You'll know that in our future discussion. So ano ba yung significance ng isang input impedance? So for the summary, we can use large signal model of the MOS transistor to determine the VDC, and then to get the gain, we just take the derivative of that. And then a simpler method of determining the response of the transistor amplifier to small time varying inputs will be shown with the small signal model of the MOSFET is introduced, and that is going to be the next module. So the next 2 modules, we will focus on actually characterizing these amplifiers when confined to small varying inputs. Okay, so that is so that our discussion is pretty short for today. Again, announcement: the quiz submission is postponed to Wednesday, so kindly do that. Kindly do all the exercises and submit it by Wednesday. Okay. So see you Wednesday. For Wednesday, we will just do a review. We won't start with the next module muna. We will have a short review para to prepare you guys for your upcoming exam. Okay. So have a good day, and thank you for watching.